This video is going to be about tangent circles and a good exercise in applying the triangle inequality. To review the triangle inequality, if we have any triangle with side lengths a, b, and c, then a plus b is greater than c. And we call two circles tangent if they have only one point in common. For example, these two circles, they only have this point in common, just one point, and therefore they are tangent to one another. And the goal here is to prove that the centers of these circles and the point of intersection of the two circles lie on a straight line. So we need to show that these 3 points lie on a single line. So let's assume the contrary. Suppose that it's not the case. Suppose that the 3 points don't lie on a single line. And if that's true, then they form a triangle. And we can denote the small radius by r1 and the larger radius by r2. And the distance between the centers, we can call it x. From the triangle inequality, and the only triangle we see here, we have that x plus r1 is greater than r2. Now I'm going to extend the segment between the two centers like this. I'm going to just continue it. And then I'm going to take a segment with length r1 on this extension. So this here is r1. Now from this inequality here, we have that x plus r1, which now lie on the same line, is greater than r2. So r2 is the radius of this circle, and this is the center of this circle. And the length of this segment is greater than the radius, r2. So this red point must lie outside of the circle, because the points that lie outside of the circle, when we connect them to the center, we get length greater than r2. The points that lie on the circle, when we connect them with the center, we get distance exactly r2. And the points inside of the circle, when we connect them with the center, we get distance smaller than r2. And because x plus r1 is larger than r2, then this point must lie outside of the big circle. But with respect to the smaller circle, the distance between this point and the center of the smaller circle is r1, and so this point must lie on the smaller circle. And so we got these two statements, that the same point lies outside of the large circle and on the small circle. And because the small circle is fully contained within the large circle, then there doesn't exist a point outside the large circle that lies on the small circle. And so that's a contradiction. And the contradiction comes from the assumption that these 3 points don't lie on the same line, and therefore they do. And that's how we proved by contradiction that these 3 points lie on a single line. And the reverse is also true. So suppose we have 3 points that we know lie on a straight line, and we construct a circle with center here and radius this segment, and a circle with center here and radius this large segment. Now we need to prove that these two circles are tangent to one another. We're again going to prove this by contradiction. Suppose that there exists a second intersection point between the circles, and then because it lies on both circles, so in particular it lies on the small circle, we know that this length here is r1, and this here is r1, this here, let me call it x, and then the length of this segment here will be r2 because it also lies on the larger circle. So by the triangle inequality, for the triangle that we see here, we have that x plus r1 is greater than r2. But on the other hand, we know that this large segment here, this is the radius of the circle. And we divided this segment into 2 parts, one x and one r1. So we have that x plus r1 equals r2. And these two statements are in contradiction. So it's not possible that the two circles have a second intersection point, and therefore they're tangent circles. The optional problem would be to solve the analogous problem, when we have two circles that are tangent, but one circle lies outside of the other circle, so they're externally tangent. The other ones are internally tangent, and these two are externally tangent. We need to prove that the 3 red points, so the center of this circle, the tangent point, and the center of the other circle, lie on a straight line. And the solution is exactly the same. We just need to assume that they don't lie on a straight line. So assuming we have a triangle here, that this is a triangle, and then the distance between the centers is x, and this radius is r1, and this radius is r2, we get r1 plus r2 is greater than x. And then we take a point here, such that this distance here is r1, and so the remaining distance here is x minus r1, because the point lies on a segment with a length of x. And we have two things, that this point here that we just drew lies on the small circle, because the distance to its center is r1, but it also lies inside of the large circle, because the distance between it and the center of the large circle is x minus r1, and x minus r1 is smaller than r2, because of this inequality. We can put the r1 on the other side, and then we get x minus r1 is smaller than r2. So this segment here is smaller than the radius, and so at this point, both must lie on the small circle and must lie inside of this large circle. And that's clearly not possible because the small circle is fully outside of the large circle. So such points don't exist. And therefore it's a contradiction, and the 3 points must lie on the same line.